announcement. So I hope everybody knows by now that June 29th is a very special day. We're going to have a Hadoop Summit at the Hyatt Santa Clara. We're doing a raffle. I hope everyone put their tickets inside, and during the evening we'll choose a few winners for a free ticket to the Hadoop Summit. We're also doing some promotion, a special discount if you register with this code in the next 48 hours. So do it quickly, it's just for folks who arrive here. And a reminder that we have 10 days left for submitting presentations requests for the summit. We got a lot of requests, we're looking for more. So please take the remaining 10 days and submit a presentation for one of the tracks. We have 3 tracks, developers, applications, and research. You can also, I advise to subscribe for the Yahoo Hadoop blog. We're posting agenda updates and some announcements there regarding the summit and also regarding the user group. As well as obviously a lot of interesting stuff that's happening on Hadoop on a regular basis. So it's worth subscribing to this blog. With that, we'll go to the agenda of tonight. We'll start with Vish from Yahoo Mail. He's going to describe how Hadoop helps to fight spam. With some nice illustrations of cats and mouse. Then Facebook, John from Facebook is going to describe HBase and Hive and basically the part of the ecosystem of Hadoop and how the integration works and what are their plans moving forward. And we're going to conclude with Ken from Bixolab that will describe how they built the terabyte dataset project on Amazon EMR. So I hope you'll enjoy the evening, and I'd like to invite Vish, please.
All right. My name is Vish. I am one of the people who works on the Yahoo Mail team. I manage a few projects within the Mail team. So I wanted to do a quick audience poll. How many of you know what yokai are, or you've done a search or whatever, wiki lookup? Nobody? Oh, you can't hear me? Okay, that's a better answer. I was asking how many people know what yokai are? Anybody did a search? You saw the title. So did any of you look up what yokai are, or a wiki search maybe? No? Okay. So I can describe that a little bit. Yokai are shape-shifting monsters in Japanese mythology. It's that you'll quickly know why I use that term in the presentation. I also want to do another thing. I want to do an audience poll for what the perception is on Yahoo Mail anti-spam. How many of you think Yahoo Mail anti-spam today sucks to you? I'm sure all of you are Yahoo Mail users. It completely sucks. Not a single person? I have a happy audience. Okay, a few, I can see a few. Okay, so there's some coming up, okay. All right, so I'll address what we're doing about it, and you should be a happier person end of this talk. How many of you, obviously the rest of you think it rocks? That's great. So those are just a picture that we picked up on what the yokai look like. I'm going to breeze through most of this stuff. So the agenda for the talk today is to talk a little bit about what shape-shifting spam means, what is the problem statement, what is it that we're trying to solve here. We'll do a little bit of a deep dive into the architecture of anti-spam systems as it's been implemented over the last 7-8 years. And then we'll look at Hadoop application in the domain. We'll look at a few specific algorithms that we think are novel and interesting to be applied in this domain, especially on Hadoop, and we'll go with that. And finally conclude with a few resources that you can take away from the presentation that you can go and play with. So have is shape-shifting spam. There are 4 variants here. All of them are visually very similar. You can see a URL in here that is a spam message. They have, the way this gets generated is through a template. A botnet is controlled by a bot master who codes these messages up in a template and then replaces parts of the template with random strings, payload information. In this particular case, there are 4 different URLs, each of which is a payload. The problem with this particular variant of spam is that it looks extremely similar for a human. The visual perception is very good, so you can say that they're all very similar. Structurally, they are similar too, but for a machine looking at each of these different variants, it looks quite different. The URL in it, if you expanded the content from that URL, it would be very different from the URL in the second one and the third one and the fourth one there. So it becomes a challenge to tie all of these messages up, and especially making a machine learn that all of these are very similar messages. A similar example here, all fairly similar in structure, delivered via bot master controlled template. And that word there, Viagra, pay close attention to it. There's a // to make a V there. And this is the kind of challenge that we face. So when people ask, hey, there's an obvious Viagra message that I got, well, if you pay closer attention to that message, it's not quite as obvious as it seems to be. I think there are a pentillion different ways to generate the word Viagra with all the characters in the word. So, anchor text and things like that, they don't work. So that's what a machine sees. This is what a human sees. ASCII art, fun to make. And there are the variants that we have picked up from our email stream. Not all of this, thankfully, is in our email stream. So some portion of it that is coming into Yahoo Mail. How many of you have seen this one in your Yahoo Mail? That's a Canadian pharmacy. So that's the 6-pack for you. And so what's interesting about all of these variants is that in addition to being a challenge for machines to parse and to learn common characteristics about, in security there's a notion of targets of chance and targets of choice. Targets of chance are small domains, your small business. A spam coming out may say, okay, let me add an email address in there for a random domain that I don't know anything about. It's not meant to be engineered in a way where we're trying to break into the domain where it's just by chance that we are sending spam to a domain. Most of your corporate domains are like that. Most of your little businesses hosting domains are things like that. Yahoo Mail is a target of choice. What that means is that there are spammer communities out there that are trying to defeat the system, constantly probing to see where the weakness is, constantly changing the templates, changing the payload, changing it in a manner where they exploit a known vulnerability within the system, or they are trying to create new cases where the system would fail and then they have a free entry into the system. So it's much more difficult to operate any system that is a target of choice. Clearly, people are probing it constantly. A small team of 6 engineers sitting behind it cannot compensate for a large community of spammers sitting out there trying to defeat the system. So you need great tools, and that's where Hadoop comes in, and we'll talk a little bit about that in the later section of the presentation today. So what does a typical attack look like? So this is real data, by the way. So this is the traffic that we saw from one IP address spread across time. So they're constantly probing and trying to see what's available. Maybe they got a free pass into the system, and they utilize all of that free pass. Our system reacts, catches them, puts them to the next bucket. They use that for some time. Our system reacts again, figures out that this is a spammer, goes away, low-level probing after that. So this is not uncommon. Most of the IPs that we see are exactly of this profile. So any system that is developed to compensate for this needs to know that this is sort of the attack vector. So that's an interesting one. This is a recent one, in fact. The size of this message that was coming into our system was 252 kilobytes, and the style tag was 200 kilobytes. So, and it's just random text in the style tag. The goal of this is that if you had any algorithm inside of it that looked at content and looked at diversity of content, looked at parsing it in a structured manner, almost all of it would get thrown out. In this particular case, they were utilizing a buffer attack where we had a smaller buffer than 200 kilobytes for the style parsing, and they were overflowing that buffer, making the message get classified as unknown, and it would bypass most of our spam filters and get into your inbox. And that's a different variant there, but essentially of the same type. So that is the view of a botnet command control center. So this is how you generate spam. You just go to a web UI. This is localhost, but there is a web UI. You can say who your recipient list looks like. You generate a template. You click a button. This TPL file is a template file, and you add random text in there. You can write a little grammar for how to generate some of the strings that you want in the payload, and that's it. You press the add button. You rent a botnet. It costs a few dollars per hour. You rent as many bots as you can, and you generate a spam campaign. It's as easy as that. And this is what we're up against. So this picture is interesting. I mean, the whole goal of putting this picture in this presentation was to show that we are constantly trying to plug holes in the system, and it would be much better if we had more fingers. So hopefully we could plug more holes in the system, and even better if we could put a rock in front of it so there's no water leaking out of it. So we'll talk a little bit about what that means for architecture and for usage of Hadoop. So why is this problem really hard? So yes, there are many variants of the message. Yes, it's a well-known problem. Any spam system should be able to do it. At Yahoo, the scale problem kicks in. We do 25 billion connections a day, 450 mailboxes to deliver to. That's not easy to do. It takes a lot of machines. It takes a lot of architecture. Obviously, when you put so many complex components in place, it gets really difficult to do it at scale. The other issue with spam is that many of the anti-spam systems are feedback driven. You wait for users to say something about the sender. That's not going to cut it in the next generation, because guess what? That 1 hour that it takes for a message to come into a user mailbox, the spammer is going to utilize that 1 hour before the first feedback comes in to send as much spam as he or she can. So that's not going to work either. The other issue with feedback is that it's extremely noisy. So if you go look into the Yahoo feedback stream for what is called spam, everything from Intel.com newsletters to Amazon purchase orders to messages from your mom are in there. So it's not easy to, it's not a simple heuristic that you can derive and say the first feedback message that came in, I'm going to simply put it in and make the sender spam, the content spammy, and so on and so forth. There's a fair amount of noise cleanup that you have to do, and it is very difficult to do. More than anything, I think it boils down to spammers being very clever and targeting us in a particular manner, and changing the spam campaigns in a manner where the system takes a little more time to react. Discovering that campaign takes effort, people involved, algorithms involved, and most of these algorithms are not, the earlier generation of algorithms were not reactive enough to be able to catch that in time, and that time is very critical. Most of the spam comes in during the time that we actually realize that this is a spam message, during that 2 hours, 3 hours, 6 hours that it takes for us to realize, the system to realize, people and systems to realize that this is spam. That's when most of the spam comes through. And most of the spammers have gotten smart these days, and they hide behind ESPs like Hotmail and Google and even Yahoo. So one of the ironies of working in this domain is that we send the largest amount of spam from Yahoo into Yahoo. So let's look at the first generation of algorithms. I'm sure you've seen many blog posts about this, that, hey, I put a simple heuristic on my mailbox. I was able to clean up 99% of the spam. Yes, works on a per mailbox level, especially if you're not a target of choice. Doesn't work beyond a certain period of time. So, and it's extremely difficult and expensive to manage. I think that's the more important piece for Yahoo, that at scale this does not work. So up until 2004, 2005, I would say, most of the systems that were in place were basic heuristics, blocks, and blacklists. Even today, there are parts of this architecture that you can see in little domains. You can see it in corporate servers, firewall rules, things like that. Essentially, that's what most people use, and when you're not, like I said, a target of choice, it works. The second generation, or maybe generation 1.5, added in what's known as the analyst track. You would take heuristics and blocks, you would put people on top of that, and have them generate ad hoc queries and work as a human resource that would look at what's happening within the system, fine-tune it, constantly keep working on it. Again, the basic problem is it's extremely reactive, usually very late, and it takes a lot of money to implement. So the second generation, this is somewhere between 2004, I would say, to 2000, maybe even up to 2008, we saw many of these generation 2 systems. What are generation 2 systems? They mainly are composed of two types of models. One is an online reputation model. An online model being that it rapidly computes every message that comes into the system, increments some counter out there. It's changing the ratio. It's changing some other piece of data. Very fast to implement, very easy to do, but essentially the problem with these systems again is that they're not very expressive. So for some of the more targeted spam attacks that we've seen these systems fail, and it takes a lot of sort of fine tuning to make it work as well as you need to work. And that's the challenge with online reputation models. So people said, okay, fine, I'm not going to go with online reputation models. I'm going to throw a machine learning classifier on top of it. Well-known solution, batch train it, every day accumulate all of the feedback that came from your users, train a classifier, and say, hey, classifier, tomorrow's feedback, tomorrow's incoming messages, put them as spam or ham. Easy to do. The one issue with batch train models is that it's hard to control them. It's essentially a black box. You take a support vector machine, you take a Bayesian classifier, you take any classifier, you give it some training data, and you say, please do what you can for me. You have really no well-managed control over what that machine does. If it doesn't do what it's expected to do, let's say it leaks spam, you have only one option: train it more, tell it more, give it more data, and say, can you please now do the same thing that you did, but in a better way? And that's basically what it boils down to. So, and that model is still relevant, I think. That it's not completely gone away, but we need something in addition to the basic machine learned models. We need something that has operator control, that can give you compact insights into what's happening in your system. The other obvious sort of drawback within the batch train models is that they're slow. It takes a while for them to learn particular variants, and even if you update them every day, every hour, it clearly cannot keep up with all of the new variants that a bot master with that really elegant UI is able to generate. So it can cover maybe 90% of your cases, but the last 10% of your spam, you still have to do something extra. So the title said yokai versus the elephant. I didn't ask you guys what the elephant is. I hope everybody knows what the elephant is. So yokai, we have figured out, we have seen some examples of it, and we've seen what the shortcomings are of the current generation of systems. fairly introductory, let's say what Hadoop is and so on. I should skip those slides? Yeah? Okay, cool. Sounds good. Skip, 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 skip. All right. So let's take a minute here and review our design goals. We know that classifiers are notorious for lack of explainability. Um, they're difficult to build, difficult to tune, and what we want to build is essentially a system that analysts and engineers can interact with, and that can summarize information and things happening within the system, compact the information, summarize it in a manner where humans can digest it, react to it if needed, but let most of the work be done by machines. Providing that insight is really critical, and I'll come to where it really helps us. The second piece of our design goal here is signal amplification. Like I said, some of those variants are coming in at very, very low volumes. So imagine a distributed botnet attack. Your payload is being generated from 100,000 IPs. Each IP doesn't have to do that much work to generate a million spam into your system. So when you now break it down on a per IP basis or on a per sender basis, the signal that you're looking at can be very, very tiny. So what you need to do in your next generation systems, and what we are working on, and that's where Hadoop kicks in, and I'll give a few examples of that in the algorithms that I go through, are take a little piece of data. If that piece of data is useful in spam classification, amplify it. Amplify it and discover other related pieces of data, bring it all together, summarize it in a manner where you can now say, oh, that little piece of data fed a huge piece of insight into the system. That is critical. Obviously, we want standard reporting, canned stuff that an analyst can digest. We want to do ad hoc queries as well. We want it all free. So that's what we're aiming for. So we built an analytic platform, and this is still in its nascency. So that's why I asked how many people think the Yahoo Mail anti-spam system sucks today. As this analytic platform rolls forward and rolls out into production, you will see that perception change. I expect it to change very, very rapidly for most people. So we use Hadoop for our MapReduce implementation. Our feature engineering boils down to very simple, very easy to manage Perl scripts that extract pieces of data from our data sets. We use big standard stuff. The one piece that I'd like to point out here is Mahout. I don't know what the awareness level of the Mahout libraries are within this group, but we found it to be very, very useful and fairly scalable. So Mahout is an open source data mining library managed by the Apache Foundation, and you can get a stock implementation of that and use it in Hadoop, and it'll do most of your data mining tasks for you. The good thing about Mahout is that it is implemented as most of the algorithms within Mahout are implemented for Hadoop. So if there is a variant of an algorithm that can be parallelized, they've chosen specifically that particular variant rather than a non-scalable variant there. So that you don't have to spend that time in researching 10 different variants, 10 different implementations, and picking the one that has good scalability properties. We obviously use a lot of proprietary algorithms on top of Hadoop, and I'll go over one type of algorithm for each. So we run basic standard reports on it. One of the problems that we face in anti-spam is what we call gaming. Gaming involves people giving spurious data to us. So this is a spammer who's created a yahoo.com account and then pumps a bunch of spam into that account and then clicks the not spam button to give us feedback to say this is not spam. Majority of our not spam feedback is dominated by that kind of spurious data. So we obviously have been interested in cleaning up that data and making sure that our reputation systems don't get affected by that spurious not spam feedback. And I'll show one of the algorithms that fixes this nicely with Hadoop. So here's a basic canned report, and you can make out this is fairly easy to see most of the most of the stuff here shouldn't be making it in. I don't know if any of you have been hit with that spam, but so we run a lot of ad hoc queries too. So we separate our implementation out into two different Hadoop grids. One grid for ad hoc querying, one grid for algorithmics, and we do a lot of ad hoc querying that are fairly interesting, and the queries themselves are actually quite novel in terms of what they're looking for. One of the things that, for example, that we find very useful is all messages that has all the messages that have just one URL in them, and that URL has a very low page rank, and that URL is occurring in our data stream at a rate where something's up, right? So an example would be amateurmatch.com, low page rank, coming in at 1.5 million messages per hour. What's up? So that's the kind of thing that we want to do. So I'll talk about two specific examples of algorithms that are implemented on Hadoop today. Discovering a spam campaign is a lot of work. So while it's easy to see some examples of it, doing the forensics to say, can I tie all of my data up into a compact campaign? Can I track that campaign day on day, week on week, and see how that behavior of that campaign is changing? Who is the bot master? Can I know his name? Can I know his phone number? Maybe not that. But maybe tracking all of this data in a manner where we can say this is one campaign and it's morphing and it's changing, that kind of deep forensics, it's a lot of work involved. So we want help from algorithms, automated systems that can provide that insight to us. So one of the algorithms that we were curious about and that we implemented last year was this algorithm called frequent item set mining. People in the data mining community know this very well. It's a classical algorithm. There are multiple variants of it, and I'll go over a little toy example that will explain how this algorithm itself works. One of the key things about this algorithm is that it's easy to implement in a MapReduce like environment. And there's a particular variant of this called parallel FP growth that is actually very, very nice to implement in Hadoop. And guess what? The Mahout library does it in parallel FP growth, so it's very easy for me. I just need to make a function call or a instantiate a class. So I'm going to go over the exact details of the item set algorithm. So imagine that your database consists of, 15 different items. In this particular case, maybe it's just 5. Yeah, 5. 5 different items. An item, to really tie it up practically, is maybe an IP address that the mail came from. It's a URL inside the message. It may be the size of the message. It may be the sender. It may be a particular anchor word. And any of those things are fair calls to be called an item. So each message in our particular case is made up of n number of these items, and we are interested in knowing, is there a pattern within our data set? Is there a pattern in our stream that would say that many of these items are co-occurring in the stream, or they're occurring more frequently, and what those frequently occurring item sets turn out to be? So the way it works is actually fairly simple, and people who've been using Hadoop will immediately relate to this and say this is actually parallelizable in a nice manner. You scan your data set and you make a count of all of your items. In this particular case, for the toy example, I found that item 1 6 times in the data set, item 2 7 times in the data set, and so on. And then you generate all combinations of your items. So you would go down to the next level. So this is pointed out in generate C2. You would do I1, I2, I1, I3, I1, I4, I1, I5, and you do a second count again of how many times those item sets have been found in your data set, and so on and so forth, until you stop and say, I've found all of the 2 item sets, I've found all of the top 3 item sets, I've found all of the top 4 item sets, all of the top 5 item sets. So it's just a glorified type of sort, but with enough power in it that you can do things that are far more expressive than a simple sort. So, and we'll see what happens when we apply this algorithm on our data set. There are a couple of caveats here with this explanation, that there are a couple of good properties about item set mining that allow you to do this in the way it's being explained. One of the properties is that any item set the target for the next item set counting has to already be a frequent item set. So to quantify that a little more, look at L2 and look at C3. Obviously, if you take all of the combinations of L2, you will end up with data sets, item sets like I4, I2, I5, right? I4, I2, I5 should be occurring. But in C3, which is our next 3-item frequent item set, I4, I2, I5 does not occur. The reason why I'm able to eliminate I2, I4, I5 as not being a frequent item set is because I4 and I5, that tuple doesn't occur in the L2 frequent item set. So every single item set, like an I2, I3, I4, every subset of that item set needs to occur in the previous tuple as an item set. So you can progressively reduce how many item sets you're counting. And when you parallelize this, because this is a counting task, it's very easy to parallelize very nicely. When you parallelize this, you can do some really fast scalable algorithms with it. And you can go deep into the data set and you can discover frequent item sets that are 25 item sets long. You cannot do that offline. You cannot do that even if you had a huge set of boxes and you didn't have a computational paradigm for it.
What is support count? Does that mean complaints?
That is support count is an artificial number. What that implies is how many do we need as a minimum to qualify it as interesting, quote unquote interesting, whatever that interesting turns out to be. So the way you generate support counts in our particular case is you say, hey, today I've received 10 million spam messages as feedback from my user community. Let's start with a 1% sample. Or so in this particular case, it will boil down to 100,000. So 100,000 is the support count. If an item doesn't occur 100,000 times, I'm not. So I would start with that. So that will allow me to keep my total item set count to a manageable level that humans can digest and work with. So let's look at the application of this. This is on 1 day's spam reports that we got. So look at row 4 and row 5. Sorry, row 4 and row 3. Look at the from user. Both of them they're saying sales. Look at the subject though. Car dealers compete on new vehicles in row 3, and row 4 has January 18th credit report update. The URL inside of that is different. One of them says sharegate.info, the other one says whatever, right? And the IP address is both the same. So now you're able, when you pivot this data on either the sender, in this particular case the IP address, or from the from user, when you pivot this data set, you are now getting 2 campaigns coming out from the same IP address, 66, 206, 25, 227, and you know exactly what those campaigns are. So you can pivot on any of those things, and you'll get brand new campaigns that have been discovered in your data set. The left side column number 2 there is the number of messages that we got from our user feedback. And again, there's a nice holistic view of it, which says that all of these are being delivered in 2,500 payloads or some multiplier of that. Again, that's what ties it up for a human being. You're able to now see that this is a campaign. You're now able to track it. You can track that particular IP address 62.206.25.227, and you can say what are the different variants it's generating going forward. That's the pivoting portion, and you can get multiple campaigns discovered from that single IP address. So yeah, so 2 examples there that I was just talking about. So we saw a pretty neat application of the frequent item set mining algorithm to discover human understandable campaigns within spam datasets. The next one is a little more exotic. What we're trying to do here is to identify spurious feedback, that not spam. Like I said, most of our not spam feedback is from spammers, ironically. So we're trying to identify that not spam feedback and eliminate that. So I'm going to breeze through some of this because it's not very easy to explain this in a short talk. Essentially, what we try and do is to model the whole ecosystem as a bipartite graph, and we consider 2 sets.
Well, if 90% of that stuff indicates spam, wouldn't that be a
utilize that to say whether you're a spammer or not. That's interesting. Yes, it is. Yeah. So we model the problem as a bipartite graph, and we say there are two sets of entities here: you and we. You being users, we being IP addresses that they're claiming to be senders of good messages. These are not good messages. This is spam, right? So in this particular case, I just put a picture out there. Y1 and Y2 are two. I have a typo there. It should say Y2. They're two different users, and both of them have said IP1 sent me good messages, and IP2 also sent me good messages. Similarly, user 2 is saying the same thing. Hey, IP1 and IP2, both of them sent me good messages, right? So both of these are clearly spammers, and in this particular case, we want to identify them. So what we do is we model it as a bipartite graph, and then we do something called graph squaring. Graph squaring just identifies a compact cluster of users who are voting against a particular set of IP addresses. Think of it like a clustering algorithm. So you bring all of these users together who seem to be agreeing to vote upon a certain set of IP addresses, and you call that a squared graph, and the weight of that squared graph tells you how many spammers are there in that clustering cluster that you've just discovered. And you then again track them, and you say, hey, I found a cluster of users, all of whom are generating not spam votes against the same compact set of IP addresses. Let's track them. And you start tracking them, and you discover new IP addresses that they're constantly voting on, saying, hey, I got more not spam from IP3, I got more legitimate mail from IP4, and we are happy to accept all of that feedback because we know they're all spammers, and we're just tracking them really closely on the grid with which batch updates of who these spammers are, and every time they give us not spam feedback, we say thank you and we accept it. So this is what the number looks like. So there are, in this particular case, row 1 says there are 100,000 different accounts that voted on, that gave feedback saying some 56 set of IP addresses are sending legitimate mail. And out of those 100,000 odd users, I think pretty much everybody was untrusted. We have a notion of a trust in the system. Everybody was untrusted. And the number of messages that they were able to pump into the system as feedback was 6.1 million in a day. That should rest the case for why we need to track them and what we need to do with that data set. So that algorithm that we use to do this, the graphing and squaring and things like that, it's called the connected components algorithm. We apply it on our not spam data set, and we discover these users, these spammers, and we track them closely. And that allows us to be, like I said, human digestible data, easy to see what's happening in the system. It's a layer on top of machines, but it's easy to automate as well. So we're more than happy to sort of implement these kind of systems on the grid today. So a few quick conclusions before I take questions on the presentation. We've had a fair amount of success in applying very stateful algorithms on the grid. Like I said, the previous generation, most of these were fast, highly scalable algorithms that couldn't maintain too much of state information. So, for example, it couldn't maintain the state of 1.5 million users at any given simultaneously for any given point in time. We wanted to change that, so we were looking for a system that had a significant amount of memory storage, whatever you want to call it, associated with it, and a computational capability on top of that, a framework for solving it that would allow us to utilize commodity hardware to drop on huge computational resources that can, and also parallelize some of these algorithms. So 3 separate goals: pick parallel algorithms, use the computation that comes with Hadoop, and get enough data stores so that you can maintain large memory algorithms that can work on highly stateful information and come up with deep insights that most other previous generation algorithms couldn't. And obviously, we are also using the grid for most of our ad hoc queries and reporting, and that's a big freebie that we get on top of all of this. So there's a standard apply slide that is part of. So this presentation, I gave this at RSA this year. So it's a reuse of that. You need to give an apply slide which allows people to go back and play with it at questions now. If there's something that we couldn't discuss earlier during the talk, I'm happy to answer any questions you have.
Yeah, so, yeah. Doesn't the isn't there still a significant window from the time the campaign begins to when you can identify it as spam, since you seem to be still relying on analyzing delivered messages as whether or not they're spam?
So I only gave a sneak peek into what we do. I couldn't disclose the whole details of it. We do run similar algorithms on our inbound traffic preemptively. So as soon as we receive a message, even before we get any kind of feedback from the users, we run fairly similar algorithms to analyze what's connected, how are they connected, what are the clusters that we see in them, domain-based clustering, and all kinds of other rules on simple traffic that comes into the system as well. That is not reactive. That one allows us to see in near real time. It's not quite real time, but every hour or so we're able to see how our previous hour's traffic looked like and what were the patterns in that traffic. Unprecedented for us. Does somebody else?
Do you use the frequent item set mining implementation in Hadoop, or do you? It looked like you were pointing to a repository in Helsinki or something. Is that just another collection?
No. So the Helsinki repository that I was pointing out was a theoretical paper that talks about the different frequent item set mining algorithms that are available. One of the algorithms is the parallel FP growth, which is what Mahout implements. We tried it out, we liked it, we saw the scalability was there for the parallel FP growth algorithm, and we chose that as our implementation solution.
Do you use HDFS for this data?
Yeah, all of this data is on the Hadoop HDFS file system.
Last question, please.
Can you talk a little bit about the setup? Is this all running in batch? How long does it take to process a full day worth of data and those kind of things?
How big's your network?
Yes. I don't think I'm allowed to disclose how big our network is, but I can definitely talk a little bit about what the computational costs are here and how much data we're talking about. Our data set itself is about 4 terabytes a day. That's what we work on every single day. But because of the time windows we use, sometimes we have to crunch data across 30-day windows, 90-day windows, so you can do the math. It turns out to be quite a bit of data. So the 4 terabytes is not all feedback data, thankfully. I mean, I'd be without a job if 4 terabytes of feedback data was coming in. It's inbound data that we get into the system. The feedback data is much smaller. So some of these algorithms that I spoke about run on much smaller data sets, but are more the algorithms that I've not spoken about today run on much larger data sets than what we typically do for feedback. How much compute time do we need? It varies, depends on what we want to do that day. If we want to track a lot of these users, a lot of these spammers very closely, or we decide to increase our time window to crunch more data, it obviously takes more compute time. We're still working through some of the details of how much that maps to on an average.
Folks, we can take a question offline, maybe. Thank you very much.
All right, I'm going to get after the topic.
John?
Yeah.
So the next session is from Facebook.